Hey Baltimore County families, thank you for joining us. I'm Miss Bond.
And I'm Mr. Bond.
And we are the Science Guys of Baltimore.
And today we're going to be showing you a video all about electricity. And I think you're going to be shocked. No, like seriously, you're going to be shocked.
Awesome, let's watch.
So today we're going to be learning about the Tesla coil.
The Tesla Coil.
This is a super cool electrical experiment. It was invented by someone called Nikola Tesla. Who would have guessed it?
Yep, and he was a Serbian immigrant to the US, and he invented lots of the stuff that we see around, including this Tesla coil.
So there are two different types of current. There's AC current, which is alternating current, and DC current, which is direct current. Direct current is something you find, say, in batteries. AC current is something you find in your wall outlet, something like that. So this is a Tesla coil. It's using AC current coming from the wall. And this is our Eiffel Tower. Yes, it is the actual Eiffel Tower. So what I'm going to do, I'm initially just going to put it on the top, and there's a small button on here you can see. The electricity is arcing through the air to get to the metal.
We know that electricity and magnetism, we say that they're kind of two sides of the same coin. So anytime you have electricity, you can have magnetism and vice versa. With the Tesla coil, if this is a negative and this is a positive, we know that opposites attract in magnets. Negatives and positives attract, and negatives and negatives
repel.
And positive, they repel. So if this is a positive and this is a negative, we know that they're going to attract. And the other thing that electricity always wants to do is it wants to find its way into the ground. So it likes to jump into other things called conductors.
I'm a conductor. This is a conductor. Even our table is a conductor. We put this plastic cutting board here to stop the electricity from flowing through the Eiffel Tower into the table. You want to give it a go?
Sure. Now a conductor is anything that's made of metal, water. This table underneath here is made of, so it goes into it. Now what do you think would happen when we shock the plastic cutting board? We're going to give it a try. You might notice that it's a little bit softer. The electricity is not able to go quite as easily through the plastic. Now this table is really big and really metal, so it is pulling it through a little bit, but not as much as that.
Next, we are going to do the same experiment. Are you ready?
Yep.
This should not hurt at all.
Why won't it hurt you when I shock this copper pipe?
Because the electricity doesn't actually have to flow through the air, travel through the air from one point to another. As it hits that point is actually when it does the damage. Go ahead. Didn't actually hurt. So if that were to be my finger, that would hurt really badly. But because my hands are firmly gripping the copper pipe, the electricity can hit here, go down the copper pipe, diffuse into my body, and be carried down to the ground. Our bodies are actually very good conductors because we're made of about 70% water. And water is also a great conductor. Well, that's why they pull you out of the pool every time there's a lightning strike near the pool. And even if I take this hand off, go ahead. We're going to touch our fingers together.
Did you hear that? It was a little bit of a shock. I can take my glove off so you can see it even better.
You should be able to see the electricity between our two fingers in 3, 2, 1.
Pretty good. You can see me jump back because I did feel it, but it's not nearly as big of a shock as if it came directly from the Tesla coil.
If we were to stand on something like a stool, that electricity would be caught in our body and it would actually shock a lot worse.
All right, Covalent, what should we shock next?
So I think we should look at this plasma ball we've got here. This is an attachment for the Tesla coil. Go ahead. Oh, excellent. And we can see plasma through the electricity. There is a vacuum, there's no air inside of this ball, and it allows the electricity to travel through to my hand rather easily and through the glass.
Cool. What's that thing?
So this is a larger version. It is also another vacuum chamber, and this electricity will easily go to your fingertips, and it looks rather beautiful if you take a look.
All right, so what else can we explore with the Tesla coil?
So we've got some light bulbs over here. I'll grab one. We're going to start off with green. We can use purple in a second. This is just a regular light bulb that you might see when you look up in your lunchroom or any cafeteria. It is covered in a green plastic case only to keep the light bulb safe and give a little tint of color. Alright, so as you can see, this side will be brighter than this side because my hands are sitting further on this side and I'm taking the electricity. Go ahead.
Alright, I want to have a turn with the light bulb, so
Go
I'm
ahead.
going to grab the other one. This time, I think we'll do purple. Alright, so I want to see what happens when I move my hands around, so will you go ahead and shock this light bulb for me?
Good.
So I noticed that as I move my hands around, the electricity is actually stopping about where my hand is. So it's flowing all the way down to my hand. It's getting lost a little bit, being taken out by me, but a little bit does continue going on throughout the light.
So why does my bulb light up?
Good question. So when the electricity goes into the end of the light bulb, the electrons on the inside turn on and they start moving around like crazy. The electrons aren't being transferred into a different kind of energy, like fire or heat, but they are just moving around a lot, and this is actually a very efficient form of energy.
Yes, this will make the light bulbs last a very long time, but you may see in your lunchroom or wherever you are that the light bulbs are flickering. That may be because of a misconnection or a short circuit. Can you see how the electricity is almost there, but not quite? Here's what it looks like when it's fully connected. So as you can see, the light is fully on, it's not flickering at all, but when it's like this, it looks terrible.
And that's what can make those fluorescent bulbs in the ceiling kind of annoying sometimes. Thank you guys for watching the video today. If you want to do more at-home science experiments, check out our website, scienceguysofbaltimore.com.
Thanks for watching.